weiterführen möchte?
All right, I can start anyways. If you ask, thank you, what the topic of my group's research is at a quite abstract level, this is what we do. We structure interfaces. And the idea is that if we structure interfaces well and we control their geometry, we might be able to either minimize or better yet, replace some of the expensive, fancy materials that are needed nowadays in energy conversion, right? Energy conversion fundamentally is always an exchange at an interface between two phases, whether it's two solids, a solid and an electrolyte, or two electrolytes. And whenever you exchange things, be it at the marketplace or in the supermarket or in energy conversion where you exchange electrons, surface area is important for exchange. Now, you will also notice that you've never seen a supermarket where the aisles are 500 meters long because it would take too much time to walk them down, right? So there's actually, increasing the length of the types, that's this kind of pointer, okay. Increasing the length of these types of elongated structures at the interface, even though it always increases surface area, at some point has its limitation because transport will become limited. And this is something that we want to investigate in a very systematic manner by controlling geometry and varying it and seeing how the performance depends on geometry. And of course, there we will work with porous materials. And if we do, then ALD will be the method of choice to provide the functional material, the red line here in my sketch. And so to start with, typically we make pores, and we've already heard about those pores yesterday. We make them by anodization. If we are to make something that is electrochemically active or electrochemically or a photovoltaics, then the electrical contact on one extremity of those pores will be very important. And to do that, instead of starting with just a sheet of metal, what we do is that we evaporate a film of metal on a conducting transparent substrate. There's some tricks to do that well. And you can see that then if you anodize that well, then you can obtain a very high degree of control. So these are the evaporated films, and then after anodization, they become transparent again. And if the length of the pores, that's the thickness of the porous layer, is on the order of some microns or even submicron, then you get colors due to interference. And the fact now that the color on each sample is very homogeneous from left to right means that the geometry is very well controlled. Here you have 5 pairs of nominally identical samples made on 2 different days, and you see also the level of reproducibility that we get. All right, and so this is what those pores look like in cross-section, and again, importantly, if they're well ordered enough, then all of them have this electrical contact to the bottom. Now we can infiltrate materials into those pores and start making devices. If you do not have atomic layer deposition at your disposal, then this is typically what the devices will look like in cross-section. This is a perovskite solar cell processed with traditional solution-based spin coating or evaporation-based techniques. And I would say it's already a pretty cool type of study because you can vary the length of those pores, try to maintain the total amount of perovskite constant so that you can compare the performance of those cells and see how performance sort of plateaus out at some level of pore length. But of course, you have this top layer on top, and it's difficult to control. And this is where atomic layer deposition now makes all the difference, because now instead of just infiltrating and filling up everything and have overfilling, now you will be able to coat the walls of those pores in a manner that has a degree of control that is quite amazing. So this is an example in battery research, and we've heard more on that than we are capable of doing. But this shows the structures. Of course, these have been removed out of the matrix just for the purpose of taking the image, but typically we keep them inside the matrix. And if you vary the number of ALD cycles that you perform, maintaining the pore length constant, then you can calculate, of course, that the loading should increase linearly. And if you actually measure the mass, then you see that it does increase linearly. Alternatively, you can maintain the thickness constant and vary the length of those pores very systematically. So you've got every single parameter in your hand. And For example, we've made silicon electrodes where the silicon, which typically has huge issues because it has this large volume change when you upon charging and discharging. Typically, it has very low durability, and here it actually holds quite well. With tin oxide, we've demonstrated that if we make this layer, well, the thinner the layer, the more accessible the material gets, and correspondingly, the higher the capacity you get per unit material, the more efficiently you exploit your material. We've done a lot of electrochemistry, electrocatalysis with these types of structures. And again, this is iridium oxide or iridium metal for oxidizing water, for electrolysis on these types of pores. And you can vary the length of the pores and increase the current that you get, or for one length, you can vary the loading. And here you can very systematically exploit or find where the optimal loading is, because if it's just a thick layer, then you can reduce the thickness without losing anything in terms of activity, of course, because catalysis is a surface phenomenon. But there will be a point where you've reached the exact ideal amount whereby you're exploiting the surface efficiently, and then lower loadings give you less activity. And from there, you can go two ways. You can go perhaps more the optimistic or academic way and say, I want to get rid of iridium here completely and go for something like rust, iron oxide. It's a terrible catalyst, of course, but by increasing the length of those pores, you will increase current. And where it becomes interesting, perhaps more on a fundamental level rather than applications, is that you will at some point, when you make the pores long enough, reach the moment where transport becomes limiting, right? That's the moment the aisles in the supermarket are so long that you just, waste your time walking around. And we've been able to demonstrate that this is really going from surface limitation to transport limitation by electrochemical impedance spectroscopy. The other direction you can take is more towards application. And one of the aspects that is important in applications is the geometry of the macroscopic geometry of the electrode. You get flow fields. And here we've worked with tubular reactors that have some internal structure. And those are 3D printed. So it's a 3D printed titanium. It's not pure titanium. It's a titanium alloy. Which we then anodize in order to increase the microscopic surface area and then coat by ALD. And you can imagine that not very many techniques would enable you to coat not only the macroscopic outside and inside of those, but also all of the microscopic length of the pores. All right, but then also wanted to work on photovoltaics. And before starting, I was worried about whether that was going to work, because as you know, if you work with catalysts, if it's impure, it's okay. It might render some of the sites less active. Very often, actually, if it's imperfect, it does increase activity instead of decreasing it. But with semiconductors, any impurity will kill you, basically. So we worked with the type of cells which I think are well suited to ALD approaches, or vice versa, namely with the so-called extremely thin absorber cells, where basically it's a, you would, from physics, you would just say it's a p-in heterojunction. Instead of having silicon being in charge of everything, absorbing light, conducting electrons, conducting holes, now you separate the three jobs to three different semiconductors. One must be good only at absorbing light, one good at conducting electrons, and one good at conducting holes. And with this, you have a little bit more freedom to choose semiconductors that are good at one thing, right? And so they don't have to be this 99.9999% pure single crystalline silicon, or things like SIGs, that are quaternary phases. And antimony sulfide is something that we can deposit well by ALD. And in fact, you see, it can be made very pure. In XPS, we see a little bit of oxygen because we don't run fast enough to the XPS, but really it is pure. It's crystalline after annealing, I have to say. We deposit it at low temperature in amorphous form, and we have to anneal it to crystallize. Now, it's actually so pure that it causes issues, because sulfides, when they're very pure, they don't often bond well to underlying oxides. And so if you deposit layer, a thin layer, 50 nanometers or so of antimony sulfide on titanium oxide, and you anneal it, it de-wets completely to something which certainly you cannot make a solar cell out of. We fixed it by depositing 1 nanometer of zinc sulfide in between. So on top of titanium oxide, a single nanometer of zinc sulfide serves as an adhesion layer, and now you can anneal antimony sulfide and maintain a layer that is very thin, 50 nanometers, but completely continuous, planar, and in fact, these are the crystals. So laterally, they're up to 10 microns large. And this zinc sulfide layer remains continuous. It remains a layer. It doesn't start diffusing into the antimony sulfide, which would certainly not be desired. You can convince yourself here that it's the case. However, when we go from planar to any sort of structure, you will lose again, because now surface tension effects means that this de-wetting will occur again, and the material will sort of collect into the holes. And these are here plenty of types of substrates, non-planar substrates, where you can see this de-wetting and how dramatic that is. However, upon annealing, I have to say, just to be clear. However, if on top, so we deposit titanium oxide, then zinc sulfide, then antimony sulfide, and then zinc oxide and anneal, the zinc oxide layer basically blocks everything, holds it in place, and antimony sulfide cannot move, so that after that, you can remove zinc oxide and get to the desired crystalline but smooth or conformal continuous antimony sulfide layer. Well, if you thought that the problem was solved now, sorry, it's not, because we see that the solar cells made out of that are terrible. And the reason for that is that we find a small amount of reduced antimony near the interface to the next layer. Not good, right? Metal in the middle of the semiconductor. The reason for that is the diethyl zinc that we use to deposit zinc oxide by ALD. It's also a reducing agent, and it reduces the surface a little bit. And due to charge balance requirements, obviously you need a cation to compensate for it. And this cation obviously has to be zinc. So now we've got zinc doping in our semiconductor, and that shifts our Fermi level. Okay, so you can fix it by a preliminary oxidation of the surface of zinc of antimony sulfide by just the right amount. You have to be careful with the amount, but if you perform some exposure of this top of antimony sulfide to ozone before depositing zinc oxide, then you generate some oxidized sulfur. So you oxidize sulfides to sulfur, and if it's just the right amount to compensate for that, then you get back to something that has, let me check where it is. So too much is not good. You make sulfates at the surface that's not reversible, but just the right amount. You see that now you're able to completely remove this zinc doping to get back to the same Fermi energy that you started with. If that was too much info in too short time, perhaps you can look at that. If we don't do that trick, then we get zinc contamination near the top of that layer. If we do the whole trick, no zinc. And then we can make good solar cells. So now those are the solar cells. So with ALD, we can start varying the thickness, right, very accurately. So now we look at different thicknesses of the antimony sulfide layer, trying to look for the optimum thickness, and we find that optimum at 60 nanometers. We can look at the quantum efficiency spectra and understand where that comes from, because if the layer is too thin, then we lose efficiency here in the red, where absorption is less strong, and that makes sense. We don't absorb everything, right? So when you make it thicker, then it gets better, but at some point you start losing in the blue, and the blue is where absorption occurs near the top. And there you see that, of course, at some point you will start getting transport issues again. So we get back to this issue of finding the best optimum between two aspects, two constraints that are contradicting each other. The optimum, it turns out, between these two is 60 nanometers. Perhaps more interestingly, we can also optimize the thickness of that zinc sulfide layer that I mentioned. We made cells with 0, 0.5, 1, and 1.5 nanometer zinc sulfide. And I should perhaps highlight that one unit cell is 0.5 nanometer or 0.4, I think. So we're talking about even individual atoms here. And we can find very nicely where the optimum is, namely at 1 nanometer. And using ultra-fast pump probe absorption spectroscopy, then we can also interpret that as being the moment where the layer is thick enough to prevent recombination of carriers at the interface, but thin enough to not hinder charge separation in the first phase. And now with all that, we can get back to nanostructured cells. This is a structure that we've made with a self-assembled monolayer of spheres that can now be coded super nicely with all the layers using ALD, right, which would not be possible otherwise, and which have a distance of 700 nanometers. And perhaps you remember that antimony sulfide starts absorbing at 750 nanometers or so. So 700 nanometers is exactly in the red where absorption is less strong. But if we scatter that light, it means that the light beam, instead of just going through, passing once, it will get scattered and be absorbed more efficiently. Of course, we see that also optically because those cells look nice and shiny. They're black fundamentally in diffuse light, but if you look at them under an angle, they shine. And they scatter this 700 nanometer light quite nicely. And by doing that, we managed to double the absorption exactly here at 700 nanometers, close to the band edge. And with that, now instead of using 60 nanometer thick layers, we can go down to 30 nanometers. And you will be like, okay, well, think of it. A silicon solar cell uses 300 microns of silicon. A so-called thin film solar cells, 3 microns. So that's 1% of that. But this is 30 nanometers. So that's 1% of the 1%. So in terms of consumption of materials, I think this is quite significant. And antimony sulfide has this problem that it generates quite low voltage cells. Of course, it's not fixing it, but you can sort of circumvent that issue by making them tandem cells. And we've made tandem cells here with solution processed antimony lead sulfide quantum dots, getting to beyond 1.1 volt, which is already not too bad. Where are we going? So there's some limitations of ALD, even though I love it, right? One of the limitations is the materials. Not everything is metal oxides, and ALD is very good for metal oxides and some, sulfides and nitrides, but there's a whole world beyond that, and this world contains things like silicon elements that are really hard to reach by ALD, like organics, hybrids, metal organic frameworks, and ionic solids. And ions is certainly not something that you will be able to just evaporate. And for all those, I think we have a solution, literally. It's performing ALD from the solution phase instead of from the gas phase, because those are all things, precursors that you can actually bring into a liquid phase that dissolve in solvents, organic solvents, water, you name it, even perhaps one day supercritical CO2. For example, we've deposited metal organic frameworks, MOFs. MOFs are a class of porous materials that actually need a solvent because that is the molecule that uses the space that generates the pores. Without the solvent, you don't get crystalline MOFs. We get crystalline MOFs and layers that are extremely continuous and thin and smooth, as opposed to what you get, which is really not a film with other methods. We've gotten lead halide perovskites in a level of quality that is significantly better than with solution processing methods. We've gotten very high mobilities and much higher carrier lifetimes than with spin-coated MAPI, and we've made solar cells. The other limitation of ALD, as we've heard several times, is that it's slow. And prototyping accordingly is slow. And if you've made some PV research or done some PV research, you will know that you need some statistics. So you need to make 20 cells of each type. And then if you do 10 different layer thicknesses, that's already 200 cells, right? And one cell takes a while. So prototyping is an issue. And yeah, in classical manufacturing, 3D printing has been one of the proposed solutions to that. And so if you now combine the advantages of atomic layer deposition with those of 3D printing, you get the ATLANT technology. And one of the things that it could do would be perform rapid prototyping of solar cells like Alex presented for batteries yesterday. This is the exact same picture almost. You could envision making an array of 100 solar cells on one substrate by 3D printing, by atomic layer 3D printing, with 10 nominally identical cells on one line and 10 different thicknesses of layer X along the other axis. And we can now additively manufacture the individual layers with atomic precision in the machine that is behind that screen. Of course, that means we have to transfer ALD chemistry to what we call ALAM chemistry, atomic layer additive manufacturing. And that it is doable is demonstrated here. We've developed some of the processes. For zinc oxide, it turns out that we started with diethyl zinc and water, like everyone does. It's one of those beloved precursors in the ALD community because it's so reactive and so volatile. It turns out here that we started having issues because it was too volatile and too reactive. And that says something about how material efficient ALAM is with respect to ALD. We actually, the material consumption is extremely low. Okay. So we decided to use a precursor here obtained from Anjana Devi in Bochum that has lower vapor pressure, lesser reactivity. And we first did the ALD study, and you measure growth rates, you get an ALD window. We also observed that it's crystalline with a preferred orientation that depends on temperature, with a morphology that slightly depends on temperature. Then you transfer that to atomic layer additive manufacturing. And it's completely identical. You get the same growth rate, you get the same temperature window, you get the same characteristics. Okay, so ALD and ALAM are the same thing at the fundamental level. And I think that's important for people who come from the ALD community because we know that it's all transferable now. Okay, but if you want to actually make the full solar cell stack with ALAM, then you cannot use a polymer like we used in the previous examples. We need a whole conductor that is also compatible with atomic layer manufacturing. And we figured out that vanadium oxide is a good one. It's actually a degenerate N-type semiconductor that conducts hole via the conduction band, which is a bit unusual, but as you can see, now we can reproduce the performance of cells that have the classical polymers with vanadium oxide, and we've also now deposited it in ALAM. You see the growth curve. This is one of those imaging ellipsometry profiles, and we have our very first atomic layer printed solar cell. And I always tell my students they have to write the labels here large enough that they are nice and readable to the audience here. If you can't read it because it's too small, it's okay, because I'm not too proud of the actual numbers. However, you see that there is a photovoltaic and there is a photocurrent, so it is a solar cell. All right, so atomic layer deposition in energy conversion applications, I think, is a very important method because, generally speaking, it allows you to perform very systematic engineering of interface.